What specific problem does the TableBench benchmark aim to solve in the context of large language models and tabular data processing?
The TableBench benchmark aims to address the gap between academic benchmarks and the practical challenges faced by professionals in real-world tabular data processing. It systematically analyzes real-world challenges related to table applications, categorizing these problems into 4 major categories and 18 specific subcategories, thereby defining task complexity based on the required number of reasoning steps. By introducing a comprehensive and complex benchmark with 886 samples, TableBench facilitates fact-checking, numerical reasoning, data analysis, and visualization tasks, which are often inadequately represented in existing datasets. Additionally, it evaluates the capabilities of over 30 large language models, LLMs, in TableQA, highlighting the need for substantial improvements to meet real-world demands, as even advanced models like GPT-4 achieve only modest scores compared to human performance. Ultimately, TableBench serves to realistically measure the reasoning abilities of LLMs in tabular data contexts, bridging the disconnect between industrial scenarios and academic evaluation.
How does the proposed method of TableBench work? Please illustrate the step-by-step process, especially focusing on the construction of the benchmark and the reasoning methods employed.
The proposed method of TableBench involves a systematic approach to constructing a comprehensive benchmark for TableQA, which includes several key steps. First, real-world tabular data applications are analyzed and categorized into 4 major categories and 18 specific subcategories, with task complexity defined by the number of reasoning steps required for problem solving. Next, a rigorous annotation workflow is established, combining manual and automated methods to create 2 high-quality corpora: TableBench, consisting of 886 samples, and TableInstruct, which contains 20,000 samples designed to instruct LLMs using various reasoning methods. The reasoning methods employed include textual chain of thought, TCOT, which derives answers through incremental textual reasoning, symbolic chain of thought, SCOT, which utilizes programming commands for logical reasoning, and program of thought, POT, which generates executable code to derive answers. Each method is evaluated to assess the reasoning capabilities of LLMs, with the overall goal of bridging the gap between academic benchmarks and real-world challenges in tabular data processing.
Can you provide a simple example that illustrates the application of one of the reasoning methods, TCOT, SCOT, or POT, used in TableBench? Walk through the key steps involved in your chosen method.
An example illustrating the textual chain of thought, TCOT reasoning method from TableBench involves solving a question based on a tabular dataset. For instance, consider a table containing sales data for different products over several months. The question could be, what was the total sales for product A in the last quarter? In the TCOT method, the LLM would first analyze the table to identify relevant rows and columns related to product A and the sales figures. It would then derive intermediate reasoning steps, such as calculating the monthly sales for product A in the last 3 months, leading to sub-goals like find sales for January, find sales for February, and find sales for March. Finally, the model would sum these values to arrive at the final answer, demonstrating a clear chain of reasoning through textual prompts that guide the model step by step to the correct outcome. This structured approach enhances the model's ability to comprehend and respond accurately to the query.
What are the theoretical or practical benefits of using the TableBench benchmark compared to existing benchmarks for evaluating LLMs in TableQA tasks?
The TableBench benchmark offers significant theoretical and practical benefits over existing benchmarks for evaluating LLMs in TableQA tasks. Firstly, it comprehensively analyzes real-world challenges related to tabular data applications, categorizing problems into 4 major categories and 18 specific subcategories, which enhances its relevance to practical scenarios. Secondly, TableBench defines task complexity based on the number of reasoning steps required, allowing for a more nuanced assessment of LLM capabilities in complex reasoning tasks, particularly in numerical reasoning and data analysis. Additionally, it introduces a rigorous annotation workflow that combines manual and automated methods, ensuring high-quality, human-annotated data that reflects real-world complexities. Finally, the benchmark facilitates a more accurate evaluation of LLMs by providing a leaderboard that highlights performance gaps between leading models and human capabilities, thereby addressing the limitations of existing datasets that often fail to capture the intricacies of real-world tabular queries.
How is the efficacy of the TableBench benchmark validated or tested? Discuss the experimental design, datasets, and metrics used to demonstrate the effectiveness of this method.
The efficacy of the TableBench benchmark is validated through a systematic evaluation of over 30 large language models, LLMs, across various reasoning methods on a comprehensive dataset comprising 886 samples across 18 subcategories. The experimental design includes a rigorous annotation workflow that combines manual and automated methods to ensure high-quality data, with a focus on real-world challenges in tabular data applications. The models are assessed using the Rouge-L metric to measure the quality of generated answers by evaluating n-gram overlap with reference answers, alongside a Pass-It-1 metric for chart generation tasks. Additionally, the performance of the models is compared against human capabilities, revealing that while advanced models like GPT-4 perform well, they still fall short of human performance, thus highlighting the benchmark's effectiveness in measuring real-world reasoning complexities. The results indicate that TableBench successfully captures the intricacies of table QA tasks, demonstrating its potential as a robust evaluation tool for LLMs in practical scenarios.
What specific results were achieved when evaluating LLMs using TableBench? Please highlight any significant findings related to model performance and comparison with human performance.
When evaluating LLMs using TableBench, it was found that GPT-4 outperformed other models in numerous tasks, particularly in complex reasoning scenarios, demonstrating commendable performance in numerical computation and analytical tasks. However, despite these advancements, all evaluated LLMs, including GPT-4, fell short of human performance, indicating a significant gap in capabilities. The TABLELM, which was fine-tuned on TableInstruct, achieved performance levels comparable to GPT-3. 5. Validating the effectiveness of the training data. Notably, the analysis revealed that while most models excelled in fact-based reasoning tasks, they struggled with numerical reasoning and data analysis tasks, particularly those requiring complex calculations and chart generation. This highlights the need for further improvements in LLMs to meet the demands of real-world, tabular data applications.